Myself, Dr. Ashwini Kumar Gupta. Today, I'll be continuing our series of basic organic chemistry, in which today I'll take lecture 13. If you remember, in lecture 12, we had done some different types of nucleophiles like strong nucleophiles, weak nucleophiles, ambivalent nucleophiles. Okay. Today, I'm continuing to further of that particular topic only, a very small fraction. So what do you basically mean by a nucleophilicity, right? Prior to starting my lecture, just I will request you to just please like and subscribe my video, my channel, and just forward this to your like-minded people. Right? I'll start my video. So today we will do with the topic, basically continuing with the same previous topic of lecture 12, a new sub part of it, nucleophilicity. Nucleophilicity. No, it's the same thing. Basically, what do you mean by nucleophilicity? It's the ability to donate electrons. Ability to donate electrons. Ability to donate electrons to an electrophile. And what are these different factors which affect this nucleophilicity? First thing, obviously the biggest factor is the nature of that particular nucleophile. That is the nature of the nucleophile. Now, in that we can see the power of this nucleophilicity. Power of the nucleophilicity increases. Increases from power from up to down, upward to down, along a group. That means along the group, the nucleophilicity increases. The power of nucleophilicity increases from along the group, from upwards to downwards. Now, similarly, it decreases from left to right. Right, along the period. The power of nucleophilicity. Right? It decreases from left to right and increases from top to bottom. Top to bottom along the group. Right? Increases from top to bottom, it increases, but decreases from left to right. Right? Right? Because see, larger the atom, since the atom is very large, the atomic radius is too large, so the electrons which are present can get easily diffused. Larger the atom, then easy diffusion of electron is easy. Diffusion of electron in the sense scattering of the electrons. Scattering of the electrons is more easy. That is, and we can also say polarizable. Is easily polarizable. Therefore, it acts as a good nucleophile. Right? Larger. That means I can say, as I go down the group, then suppose this is fluorine, bromine, and iodine. With respect to atomic size, fluorine is less than chlorine, which is less than bromine, which is less than iodine. That means iodine has the highest atomic size. Therefore, iodine becomes a stronger nucleophile. And with respect to stronger nucleophile, I is more than bromine, which is more than chlorine, and which is more than fluorine. With respect to nucleophilic character, means nucleophile has been attack of a nucleophile. It should be electron rich. It should readily attack an electrophile or donate an electron. Iodine can easily donate an electron due to its larger atomic size. Now, Why does this electron density increase in it? Because since addition of electron results in addition of shells. Therefore, increase in atomic radius. That we have read in class 10, right? Class 9th and class 10. Now what do you have? What does happen? The electronegative elements. The electronegative elements, they hold the electrons very tightly. Very tightly. Means they don't easily leave the electron. They are, on the contrary, they pull the electron towards itself. Therefore, they are unlikely to donate. Likely to donate the electron. Likely to donate the electron. Therefore, a less electronegative element is a better nucleophile. Less electronegative element is a better nucleophile. As we go, suppose carbon, nitrogen, oxygen and fluorine. Fluorine is highly electronegative, then oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. That means I can say an oxygen related group is more better nucleophile as compared to fluorine. Similarly, a nitrogen nucleophile is better than oxygen, right? Now, no wonder, if you want to increase the nucleophilicity of the particular group, then you can take, generally we can take a polar protic solvent. A polar protic solvent, what happens? It stabilizes the nucleophile. And then as it stabilizes the nucleophile, then you can enhance the strength. I'll take in the next page. As we know, fluorine it has a very small atomic radius, but if I want to enhance the nucleophilic character, then what can I do? And one more thing I know, it forms a better hydrogen bonding with water. Forms. So due to the formation of hydrogen bonding, the atomic size means it will increase, because many water molecules are being attached. Water molecules are attached here. In that way, I can say I can enhance the nucleophilic character of fluorine if I take any polar protic solvent. Because this polar protic solvent will stabilize the particular nucleophile, right? Thus I can say along the period, that is from left to right of the periodic table, as the basicity is directly proportional to the nucleophilicity, right? Means as the basicity increases, so does the nucleophilicity. If I say carbon, nitrogen, oxygen and fluorine, right? Oxygen, take for example OH minus, if I take NH2 minus, I say, and F minus if I take. No doubt OH is more basic than Cl and NH2 is more basic than OH. So NH2 becomes a better nucleophile than OH, which becomes a better nucleophile than F minus. Just make it a note of it. Why? Because oxygen is more basic than fluorine, nitrogen is more basic than oxygen, and carbon basically is more basic than nitrogen, right? So NH2 is a better nucleophile than OH, which is a better nucleophile than F, right? So fine. And what happens along the group? Along the group, basicity is inversely proportional to nucleophilicity. That means lesser the basicity, more the nucleophilicity. Lesser the basicity, more the nucleophilicity of a particular. Right? That means I can say iodine minus is more than bromine, more than fluorine is more than. That means iodine is a better nucleophile than a bromine, and then that fluorine, and then fluorine. Right? So whenever if I want to have an attack of a nucleophile, iodine will play a more important role, much better role than fluorine, because iodine is a much better nucleophile than fluorine. Why? Because iodine is less basic. Iodine becomes less basic than fluorine. Becomes less basic than fluorine. Right? In this particular group, in the particular, I'm not saying iodine is less basic with somebody else. I'm comparing iodine with fluorine. Iodine is less basic than fluorine minus. Minus Cl minus and Br. Fine? Okay? Yeah. Now we'll finish here till okay. Now we'll go to some another topic. Today we'll take a small lecture, not for much. Types of reaction. Different types of reaction. Which are the different types of reaction? Again, we'll do one by one. One is nucleophilic reaction. That means attack of a nucleophile. Attack of a nucleophile. Right? In that nucleophilic reaction, first one you can say it's an aliphatic nucleophilic substitution reaction. Aliphatic nucleophilic substitution reaction. Aliphatic means along a straight chain. I'll take R, L, living group. R is any alkyl group, and then L is the living group. Suppose this I will attack with a nucleophile. I will attack with a nucleophile. Then it will become R and U plus L minus. That means L has to be a better, much better leaving group. Then only there is point in attacking a nucleophile. Then only a nucleophile. If the L is a bad leaving group, obviously then this reaction will not take place. So L has to be a very good leaving group. Has to be a very good leaving group. Now, SN, I will say nucleophilic substitution reaction, I will write as SN reaction. They are given by those compounds. Those compounds that have nucleophiles या फिर nucleophilic groups as a living group. Right? Means the nucleophiles are also a good living group. Fine. Second thing, the living group capacity is inversely proportional to 1 upon basicity of the group. That means I can say lesser the basicity, more stronger the living group power. The power of a living group, increases if the basicity is very less. If the basicity is very less, right? Lesser the basicity, better the leaving group capacity. Better the leaving group capacity. Will this is very important. Make a note of this. Leaving group. If you have to be a good, better leaving group, then you have to be lesser basic. Lesser the basicity, better the leaving group. But if more the basicity, then the leaving group capacity decreases. As we have seen in the previous slide, where OH is a much better base than fluorine in terms of basicity. That means, can I say if OH is a better base than fluorine, that means OH is a bad leaving group? Is a bad leaving group as compared to fluorine? As compared to fluorine, OH is a bad leaving group, but OH is a better now this OH is a bad leaving group, but OH is a better nucleophile, much better nucleophile than fluorine, but a bad leaving group than fluorine, right? No. We will take some examples of strength of the leaving group. Right? That strength of the leaving group in a decreasing order. Of the ions, strength of the leaving group, right? You can say CF3 SO3 minus is a much better leaving group than bromine AR SO3 minus, which is a much better leaving group than AR SO3 minus. This is a better leaving group than CH3, which is a better leaving group than H2O plus, a better leaving group than fluorine minus, which is fluorine minus, and you can say CH3 O2 minus, right? That means I can say these are weak base. That means weak conjugate base, to be more precise. Weak base or a weak conjugate base. Weaker the base, stronger the leaving group capacity. We will take a simple example. Forget about all these. We will take of iodine, bromine. Iodine, bromine, chlorine and fluorine. Suppose if I take HI, HBr, HCl and HF. Now, as we know, HI is more acidic. HI is more acidic than HBr, which is more than HCl, which is more than HF. Why? Because iodine can easily donate proton because it has a higher atomic size, is very big, so the proton can easily part off from HI. So I can say this is more acidic to HI. Then H plus plus I minus. That means this is a conjugate base, right? This is a conjugate base. If this part is an acid, then obviously this part has to be a base, but it is known as conjugate base. Conjugate means same thing which is associated with it, the conjugate base. So conjugate base, right? Similarly, if I say HF and HF, it will give H plus plus F minus. This is an acid. This is a conjugate base. If this is a weak acid, that means this is a strong conjugate base. This is a weak conjugate base. Weaker the conjugate base, better the leaving group. Therefore, I comes first, I minus, and then comes L. I hope you might have understood this. HI, HBr, HCl, and HF. HI is a strong acid. So, if it is a strong acid, then obviously weak conjugate base, because a strong acid has to give a weak conjugate base. Similarly, a weak acid has to give a strong conjugate base. If it is a strong conjugate base, then obviously it will be a weak leaving group, because we know leaving group capacity is directly inversely proportional to 1 upon basicity. So I minus is a weak base, so it is strong leaving group as compared to fluorine, right? Just make a note of it, it's very important. Right? Okay, I'll delete this. I hope you might have understood this. Now, that means, can I say in nucleophilic substitution reaction, basicity of a leaving group has to be very less? Right? Basicity has to be very less with respect to the incoming nucleophile, which has to be a strong base, because a stronger base only can attack a weak base. If it is a weak base, then it can be easily replaced by a stronger base. That means a strong basic nucleophile, I can say one strong basic nucleophile can easily replace a weak basic leaving group or a nucleophile. Okay. That means, can I say RCl, if I take it OH minus. OH minus is a strong base, strongly basic nucleophile. If it is a strong nucleophile, then only it can replace a chlorine, which is weakly basic. This is strong, then only the reaction of ROH can happen. But if we take the other way around, if we think so, it is ROH alcohol, and which if I want to react it with a chlorine nucleophile is a weak base. It's a very weak base as compared to OH. OH is a strong. So therefore this reaction will not take place. No reaction will take place, because this is a weak base and this is a strong base. If it is a strong base, obviously then it is a weak leaving group. If it is a weak leaving group, so this guy is not going to attack on R. He is a good leaving group, so we can easily attack here and we will have fine. So this reaction is possible, but this reaction is not possible. Now, then alkyl halides. So two types of nucleophilic substitution reaction, very important. Alkyl halides show two types of nucleophilic substitution reaction. One is SN2, which is known as bimolecular nucleophilic substitution reaction, and other one is SN1, which is unimolecular nucleophilic substitution reaction. So alkyl halides show two types of substitution, nucleophilic substitution. One is SN2, other is SN1. SN1 is unimolecular and SN2 is bimolecular. I'll explain you in the today now. Further slides I will show you what do you mean by biomolecular, what do you mean by unimolecular. Now first we will go with SN2 reaction. SN2 reaction. Suppose this is RCl. This I want to. This is a strong. Yes, we can easily undergo. Fine. Now, the rate of this reaction in SN2 case, the rate of the reaction is directly proportional to the not only this but also on the strength of the nucleophile. Means this reactivity takes place on both, not only on the alkyl halide but also on the nucleophile. This is the nucleophile. The strength of the nucleophile and the alkyl halide both are responsible for this particular reaction to take place. So there are two things. Therefore, it is known as bimolecular. Why bimolecular? Because it depends upon the alkyl halide and also on the OH nucleophile. So it is known as bimolecular. But although this happens in a single step, this is a single step. In one single step, it takes place via some transition state. I will show you. Take for example H. If this nucleophile comes first, this is known as RDS. The nucleophile attack No, first thing, what do you mean by rate determining step? Rate determining step is the slowest step. Always, always in a reaction, if there is a slowest step, that slowest step is known as the rate determining step or RDS. Rate determining step or RDS, we can say in short form. Rate determining step or RDS. Now, here the nucleophile, this F in the sense formation. And B is breaking. Right? There is a formation of a new bond between nucleophile and the carbon atom, and there is a breaking of a bond between carbon atom and the nucleophile. Right? Now, I can say the reactivity is indirectly dependent on steric hindrance. Steric hindrance around the alpha carbon and or beta carbon of the particular reactant. Just make a note of it. Reactivity is indirectly proportional to the steric hindrance. That means if more the steric hindrance, the reactivity decreases. Lesser the steric hindrance, the reactivity increases. We'll take an example. Suppose if I take a simple fluorine. Now this is an alpha carbon atom, right? And suppose if I take now, just a second. Sorry, this is an alkyl halide. This is an alkyl halide, right? Now if R dash R dash. This is an alpha carbon atom. This is an alpha carbon atom, right? um, uh, just just cancel out here. RCR. Then you can see this is alkyl halide. Then hello, hello. हाँ बोलो. हाँ हाँ बोलो. अरे किसमें? हाँ डैज, हाँ हमें उसको ही ट्रांसफर करने को नहीं मिला. ट्रांसफर कर देता हूँ, क्योंकि मेरा भी लेक्चर खत्म होगा. अच्छा, आपका ये एसी खराब हो गया है क्या? अरे अभी अभी तो खरीदा था. हाँ पीसीबी होता है, वही तो मेन होता है. पीसीबी तो मेन सर्किट जिसके ऊपर हर चीज़ चलता है. कोई भी इलेक्ट्रॉनिक सर्किट है. फिर हाँ पैसे क्या हो गया? पीसीबी उड़ना नहीं हो गया. नहीं. अरे बाप रे, वो तो हाँ, तो आपने तो उसको पहले कंप्लेंट तो डाल दिया है ना. तो जो पीसीबी मिलने में थोड़ा इश्यू होता है, लेकिन क्योंकि हर हर इलेक्ट्रॉनिक सामान पीसीबी पे चलता है. पीसीबी मतलब उसका बेसिक सर्किट, हार्ट है उसका हार्ट. कितने टन का है? दो टन सफिशिएंट बिग अमाउंट. और तो फिर आईएफबी वाले को बुलाया था. हाँ हाँ. अच्छा अच्छा, लेकिन वो उसने बोला ना पैसा नहीं लेंगे. देखो भाई, कुछ बोल देना उसको कि भाई वारंटी में है, ऐसा मेरा पीसीबी मैंने डाला अभी तक आया नहीं क्या. आपने पूछा नहीं क्या उसको? नहीं पूछ लेना, बेस्ट थिंग उसको पूछ लेना कि देखिए मेरा हो गया अभी तक आया नहीं आपका, तो फिर आई एम नॉट रिस्पॉन्सिबल फॉर दैट. बिकॉज इस समय तो मैं तो पंखा बंद करके लेक्चर ले रहा हूँ. हाँ, इतना गर्म हो रहा है कि पूछूंगा. नहीं लेक्चर तो इधर ही लेगा ना. इधर फैन बंद करके इधर आधा घंटा हूँ, आधा घंटे में हालत पूरा एकदम पिघल गया हूँ. एकदम जल्दी ये फैन का इतना आवाज़ नहीं ना, फैन का आवाज़ बहुत आवाज़ है ना. वो उसमें से भी आवाज़ आ रहा है, वो पूरा सारा आवाज़ मेरा ले रहा है अंदर. इसकी वजह से मैं पूछता हूँ अभी इससे जल्दी ख़त्म करूँगा लेक्चर. मेरे को नहीं लगता इतना नंबर मैं ले पाऊँगा. हाँ ठीक है. मैं अभी ट्रांसफ़र करता हूँ, जैसे मेरा लेक्चर खत्म हो तो श्रेया को ट्रांसफ़र कर देता हूँ. हाँ हाँ मोनू को ट्रांसफ़र कर देता हूँ. No, alkyl halide. Then we will see. Then alkyl halide where the hindrance is the least. Then compared to primary halide, then secondary halide, and then tertiary. In tertiary halide, it is bonded with three carbon atoms. It is bonded with three carbon. The alpha carbon atom is bonded to three carbon atoms. This is the alpha carbon atom. When alpha carbon atom bonded to two carbon atoms, then it is secondary. If it is bonded to just one, then it is primary, and then to three, then it is tertiary. So, as we saw in the previous one, it's the reactivity. The reactivity is inversely proportional to the steric hindrance at the alpha carbon atom, right? So the steric hindrance is least in alkyl halide. So alkyl halide is more conducive or more feasible or more chances of undergoing, or the SN2 reaction or alkyl halide with the maximum as compared to the primary, which is as compared to the secondary, and which compared to the tertiary. So this is the reactivity pattern of SN2 reaction. Primary is more than secondary, is more than tertiary. That means alkyl halide is more than primary, is more than secondary, is more than. Now we'll see a very important of this is known as stereochemistry. Stereochemistry of SN2 reaction. Stereochemistry means arrangement of atoms in space. Arrangement of atoms in space. That means the 3D types. Right? Exactly. Now, I will just show you the reaction, how it is. Suppose this is OH minus. It attacks on alkyl halide, where one H is in the plane of the paper, the other H is dotted line, it's below the plane of paper, suppose. And then this is, suppose you can say, an ethyl group. CH2, CH3, ethyl group. This is pointing towards the observer. This is below the observer, and this is in the plane of the paper. And this is the bromine. Fine? No. This OH minus is strongly basic. So this will attack on backside of this carbon atom. The moment it attacks, then this bond will break, as we have seen in the the transition state I saw you, the formation and breaking. Here, as soon as it attacks, this has to part off, break. Then OH will be bonding to carbon. The moment it bonds to carbon, what happens? There is a shifting of bonds. The moment it on this bond which is on the back side gets shifted, its position changes. Its position changes, and this remains and this remains CH2, CH3. Right? There is a change in stereochemistry. The arrangement of atoms. Previously the atom was backside, this hydrogen, now it has backside, but now it is on the backside only, but on the other face of the carbon atom. So you can say the stereochemistry has changed. The stereochemistry has changed. And plus the Br minus is released. Fine, this is important. O attacks on the backside. So then there is a formation of OH and there is a breaking of this. The moment it breaks, this reaction happens, this particular bond shifts to, you can say, roughly you can say it takes a 180-degree turn from here. Previously it was here and now it has gone to this place. And then now the whole, this has changed. This is known as, you can say, one propanol. And I can say this as 1 bromopropane. 1 bromopropane gets converted to 1 propanol, right? Here I can say this is a nucleophile. The nucleophile attacks from the backside, causing a change in the configuration. Configuration means arrangement of atoms. Change in the configuration, the arrangement of atoms. This particular atom, which is back, it gets approximately 180-degree shift it has, and it goes on the other side, right? Change in the configuration, and we get you can say it has a inverted configuration. Inverted configuration. As you know, in the previous lectures I have told you there are two types of configuration. One is retention of configuration and one is inversion of configuration. Retention of configuration means as was the reactant, same is the product. The position of the bonds as it is in the reactant, substrate, similar the same is the position of the particular bonds in the product also. But that is known as retention. Retention means as such it has retained. But inversion or inverted means the position of one of the bond has gone to the other side. The position of that particular bond has changed, completely changed. So it's known as inversion of configuration, or Walden inversion also it is known as. Walden inversion. Walden inversion. inversion of configuration of Walden inversion. Fine? No. Okay. No. You can say this SN2 reaction is favored by strong nucleophile. The nucleophile in this case has to be very strong. Nucleophile in this case has to be very strong, right? And also a polar aprotic solvent. Polar but aprotic solvent. This is very important. Polar aprotic. Aprotic means the one who does not contain any proton connected to oxygen. Connected to oxygen or nitrogen. Connected to oxygen or nitrogen. Fine? Strong nucleophile. So what? Suppose if you take a polar, example, you can say acetone. Acetone is CH3, C double bond O, CH3, or you can say dimethyl sulfoxide. It will be CH3 dimethyl sulfoxide, and then DMF, dimethyl formamide, and DMF. Formamide is HC double bond O and CH3. CONH2 we have CO and H2, so it is formamide. It's amide. CONH2 is amide group and H to formamide, but here dimethyl. So 2 H are replaced by 2 CH3. So NN dimethyl formamide. NN dimethyl form, it is, to be more precise, NN dimethyl formamide. This is a aprotic solvent. But suppose if I take a polar protic solvent, anybody, alcohol, anything. If I take a polar protic solvent, then what it forms? This polar protic solvent will form bonding with the nucleophile. It will form bonding with the nucleophile and thus decreasing the strength of nucleophile. Thus the strength of the nucleophile decreases. Strength of the nucleophile decreases if there is a bonding of the polar protic solvent. Fine. So it has to be always be done in presence of a polar aprotic solvent only. Okay. So today I finished till SN2 reaction. In the next lecture I will take you SN1, the other type of reaction. Right. I hope you might have understood this. If still you can see my lecture and you will be able to. This is all complete basic, because these type of reaction, it's very important when we further go into mechanism part, right? So I hope you might have understood today's lecture. I will meet you in the next lecture, in which I'll be taking you SN1 reaction, then comparison between SN2 and SN1 reaction, then different examples of, you can say, nucleophilic substitution reaction, types of different reactions, in which includes different types of functional groups, different types of groups, and how do those groups react towards SN2 or SN1 reaction. To be more precise, nucleophilic substitution reaction. So please do comment and visit my YouTube and the Facebook, and do follow and subscribe the channel, right? And do write the comments. You can also email me or link me with my WhatsApp number, which I have given it in the description. Okay. So I shall meet. So it's over for the day. I'll meet you in the next lecture, right? And as I have told you what all things I'll be teaching in the next lecture. Okay. So I shall take a leave. So I shall take a leave now, and I will accordingly I will explain you in the next lecture, number 14, all the different parameters of SN1 and SN2 reaction along with the difference. So let's take a leave, and I'll meet you in the next lecture. Okay. Thank you. Thanks a lot. Namaskar. Thanks.